Hi, Chris Good here. We're doing a solution to a practice repeated measures analysis analysis of variance problem, and this is the one that's labeled number 1 in this series of 3 practice problems. And let's just read through the beginning. A researcher has randomly selected a sample of 8 adults to participate in a memory study. Each adult is administered a treatment and then given a memory test. The memory test scores are standardized for comparison across drug. Higher score indicates better memory score. Conduct repeated measures ANOVA to find if, determine whether significant differences exist between drug types, among these drug types, and their effect on memory. I'm going to cross out what is the effect size here. We're not going to work on that today. Let's do a repeated measures analysis of variance. Step 1 is, of course, always state the null hypothesis, just like all hypothesis testing statistics. For repeated measures ANOVA, regular ANOVA, same as the t-test, we assume that these population means are equivalent to each other. That is, the population from which this sample was selected has a mean equal to the population from which this sample was selected, which is equal to the population from which this sample is selected, and it's the same one for this one. So mu control equals mu caffeine equals mu drug A equals mu drug B. Step 1's done. Step 2. Let's select an alpha of 0.05, just like usual, and we're going to find the critical value for F. So F crit is going to, well, let's see, it's F crit for what degrees of freedom? That's the question, really. Degrees of freedom in the numerator, degrees of freedom in the denominator. That's what you put in the parentheses after F crit. So we need to know what degrees of freedom we're going to use for this repeated measures analysis of variance. Unlike in the independent, well, no, let's do the part that's like the independent measures ANOVA. F eventually is going to equal MS between treatments divided by something. Alright, so the numerator degrees of freedom are going to be degrees of freedom between treatments. That's k minus 1, and always has been, always will be. We have 1, 2, 3, 4 treatment groups. Minus 1 is 3. So 3 is going to be the numerator degrees of freedom, no problem. But in the repeated measures analysis of variance, you don't divide by MS within treatments, you divide by MS error. And you get MS error by dividing SS error by DF error. And SS error you get by subtraction. SS error is going to equal SS within treatments minus SS between, not between treatments, between subjects. So if we get SS error by subtraction, then we get DF error by the same subtraction. It equals DF within treatments minus DF between, not treatments, between subjects. Alright, you guys know what DF within treatments is, right? That's big N minus K. That's just the degrees of freedom for this condition, this one, this one, this one, all added together. Alright, we're going to take that quantity, we're going to subtract degrees of freedom between subjects. That's just the number of subject means that you have minus 1. We have, so it's n, the number of subjects, in each condition, and it's the same number in each condition because it's repeated measures, minus 1. Well, big N here is, we have 4 conditions, 8 subjects in each condition, 8 scores in each condition, so how many total scores do we have? 32. Minus the number of conditions we have, minus 4. We have 8 subjects, minus 1 is 7. So that's 28 minus 7, or 21. So 21 is going to be the degrees of freedom in the denominator. Let's take a look at our F table. I'm going to load that up on my iPad here. Boom, there we are. So the degrees of freedom in the numerator is going to be 3, because we have 4 conditions. And then we're going to have to scroll down here to 21 degrees of freedom in the denominator, and I'm going to zoom in a little bit for you guys. Looks like 3.07 is the F crit for this. 3.07. Awesome. Next, let's work on the numerator, because that's not going to change between a repeated measures analysis of variance and independent groups analysis of variance. The numerator, did I say denominator? I meant the numerator is going to stay the same. Alright. The numerator is going to be MS between treatments. Let's do SS between treatments. That's equal to sum of your t squares over n minus g squared over big N. Now, I've already calculated the t's for each of these earlier, so I'm just going to fill those in. The t for control is 39, the t for caffeine is 50, the t for drug A is 78, and the t for drug B is 18. Alright? If we add all these together, then we should get our G, right? So I'm just going to put my calculator over here. And 39 plus 50, we're shooting an iPad with an iPhone, that's interesting. Plus 78 plus 18 is 185. So G, I'm going to write that up here, G equals 185. Alright, let's shut that down for a second. Okay, so let's do our T's. That's 39 squared over N, which is 8 scores, right? Plus 50 squared over 8, plus 78 squared over 8, plus 18 squared over 8, minus 185 squared over big N, which is 32, right? That's the number of total scores that we've got. Okay. So 39 squared is 1521 over 8, plus 50 squared is 2500. $78 squared is 6084, and 18 squared is 324. 185 squared, don't forget this is minus g squared over n, 34, 225 over 32. Alright, 1521 divided by 8 is 190.125. 2500 divided by 8, 312.5. 6084 divided by 8, 760.5. and 324 divided by 8, 40.5. Minus 34225 divided by 32 is 1069.53, and then there's some rounding in there. Let's see what we come up with. How about this? Change that to a negative and add 40.5 and 760.5 and 312.5 and 190.125. Alright. So I get 234.09 with some rounding, and that's going to be our sum of squares between treatments. You know what? Let's go ahead and get our mean squared between treatments. Actually, I already written this out on another page. Our mean squared between treatments, mean square is variance. Variance is sum of squares over degrees of freedom. So sum of squares between treatments divided by degrees of freedom between treatments. I'm going to round up to 234. I'm not going to round up. Let's just go ahead and divide 234.09 divided by 3, which was our degrees of freedom between treatments. I get 78.03. That's what I get right there. I'm going to keep that. 78.03 is our mean square between treatments. That's going to go in the numerator of our F ratio. What about the denominator? Well, MS error is different. MS error we need to get by dividing SS error by DF error. But we need to get SS error by subtraction. And the first is within treatments. Now, I'm going to take a little shortcut here. I've already worked out the sums of squares for each individual treatment. I'm just going to fill these in the table here. The sum of squares for control group, I got equal to 10.875. If you work these out yourself by hand, go ahead and check your work here. I'm pretty sure these are right. 7.5 is the sum of squares for caffeine. 11.5 is the sum of squares for drug A. And 7.5 again is the sum of squares for drug B. So those are sums of squares. The sum of squares within treatments is equal to sum of the sum of squares for each treatment. So that's equal to, add all these up, 10.875 plus 7.5 plus 11.5 plus 7.5. Alright. 10.875 and 7.5 and 11.5 and 7.5. There we go. So I get 37.375 for sum of squares within treatments. Now, in independent groups analysis of variance, we would want mean squared within treatments, but this is repeated measures. So what we're going to do is take within treatments, and we're going to subtract from it SS between subjects. How do we get SS between subjects? That's new. It's not SS between treatments, it's SS between subjects. That's different. That's equal to the sum, there's a new formula, sum of P squared over K minus G squared over big N. What's P squared? P is the participant total. Just like T is a column total, T was the total of all the control scores. P is participants 1 total, so 5 plus 7 plus 9 plus 2 is 23. 4 plus 8 plus 9 plus 3 is 24. Yeah, you guessed right, I already did these. So I'm just going to fill these in. 22, 26, 27, 19, 19, and 25. Alright? P totals are just like T totals, but they're totals for each participant. We're going to divide their squares by K, the number of groups. Hey, this looks familiar. Remember, SS between treatments is the sum of the T squares, right? The totals for each column divided by the number in each column. Sum of squares between subjects is the square of the participant totals divided by the number of scores each participant has. This is not a coincidence. It's not a coincidence. That's exactly how it should be. Let's work it out. So P squared over K for each one. 23 squared over, what's K? 4. 4 treatment groups. Plus 24 squared over 4, plus 22 squared over 4, plus 26 squared over 4, plus 27 squared over 4, plus 19 squared over 4, plus 19 squared over 4, plus 25 squared over 4, minus G squared over N. Well, I'm just going to copy this, because that's what G squared over N is. It's 1069.53. Alright, let's get out our calculator. Let's see what's what. 23 squared is 529. 24 squared, 576. 22 squared, 484. 26 squared is 676. 27 squared is 729. 19 squared is 361. We had 2 of those. And finally 25 squared is 625. And don't forget to subtract this term, 1069.53. Almost off the edge of the paper. Alright, 529 over 4 is 132.25. 576 over 4 144, 676 over 4, 169, 729. I missed one. Let's see. 132, 144, 484 over 4. That was 121. I missed this one. Okay, but it's in there now. 729 over 4. 182.25. 361 over 4 is 90.25. And remember, we had two of those. These two. And finally, 625 over 4 is 156.25. Let's make sure we got all these. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Don't forget to subtract this term. 1069.53. Alright. Let's add them up. 132.25 plus 144 plus 169 plus 121 plus 182.25 plus 90.25 and 90.25 and 156.25. It's 1085.25 minus 1069.53. 15.72 is my answer. 15.72 is the between subjects. The between subjects sums of squares. And we don't want means at squares for between subjects. We're going to use this in this equation. Sum of squares, error, that's what we want, is equal to sum of squares within treatments minus sum of squares between subjects. That's what we just calculated right here. We did sum of squares within treatments before. That was on the other page. Sorry, within treatments was 37.35. All right, 37.375. 37.375 was our sum of squares within treatments. Sum of squares between subjects was 15.72. So 37.375 minus 15.72, 21.655. That is our sum of squares error. Now we can do mean squared error. Mean square is variance. That's what mean square is the average sum. It's the average squared deviation from the mean. This is the sum of the squared deviations. And the mean squared, or variance, is going to be the sum of squares divided by the degrees of freedom. So that's 21.655 divided by degrees of freedom for error, which we already did. It's 21. Bring that back up here. 1.03 with some rounding there, and that's okay. Alright, now we're ready to calculate our final score of f, which is what we wanted all along. That's the mean squared for between treatments, not between subjects, divided by the mean squared error. Alright, our mean squared between treatments was 78.03. Mean squared error, 1.03. This f is going to be huge. Huge! 78.03 divided by 1.03. I get 75.76 with some rounding. Okay, let's compare that to our critical value for f, which is 3.07. Obviously, our decision is to reject the null hypothesis with an exclamation point. What does that tell us? It tells us that somewhere among these three group means, which we don't know what they are actually, let's go ahead and calculate those group means. So the mean for the control group was, I got the totals here, I'll just divide by the number of scores in each one, so 39. Make sure you guys can still see that. 39 divided by 8 is 4.875. The mean for caffeine was 50 divided by 8. That's 6.25. The mean for drug A was 78 divided by 8, or 9.75, and the mean for drug B was 18 divided by 8, which is 2.25. Alright. So we know that there's a significant difference somewhere among these four means, but we don't know what it is. So at this point we can say, yes, the analysis of variance, the repeated measures analysis of variance revealed a significant effect of drug treatment on memory score, but we don't know what that effect is. To find out, we need to calculate the only post-hoc test that you guys know about right now, which is Tukey's HSD, the honestly significant difference. For the repeated measures, it's a little bit different. For independent groups, it's Q times the square root of the mean squared within treatments divided by N. For the repeated measures, we use the error term for this F, which is mean squared error, in that numerator under the radical sign. So not Q equals, I'm sorry, let's start that over. Q times the square root of mean squared error divided by N, the number of scores that we have in each condition. Again, you have to have the same number of scores in each condition in order to use Tukey's HSD. But in a repeated measure study, you'd throw out any subject that you didn't have data from on all four of these treatments anyway, so it's okay. So Q. To find out the value for Q, we need to go to the Q table. I happen to have one handy, and Q requires that you look up the number of treatments that you have, not the degrees of freedom in the numerator. We have 4 different treatments, and then we go down to degrees of freedom in the error term. Now it skips here in our table from 2 to 24. We're going to be more conservative, which means we're going to use the lower degrees of freedom that's closest to the degrees of freedom value that's in the table that is the next step down from the degrees of freedom we have. We have 21 degrees of freedom. We're going to use 20 to calculate Q, which is right here, 3.96. So Q is 3.96, and HSD is Q times MS error, which was 1.03, divided by N, which is 8. All right, back to the calculator. 1.03 divided by 8 is 0.12875, so it's going to be 3.96 times the square root of 1.12875. We'll square root that. Where's the square root? There it is. Alright, so 3.96 times 0.3588175, etc. gives us 1.42 with some rounding. Right, so the difference has got to be that big. Is this difference that big enough? So is the difference between drug A and caffeine this much or better? And the answer is yes. Okay, so 9.75 minus 4.875, right? Oh, it's the same thing, that's half of it, right? So yes, that is significant because the difference is greater than this. how about between 9.75 and 6.25? That's 3.5, so that difference is significant as well. Certainly 9.75 is greater than 2.25. In fact, 4.875 and 2.25 are the same distance apart, right? I mean, it's a significant difference, is what I mean. It's greater than the honestly significant difference, right? So, all of these differences are significant, and we can conclude that drug treatment B is significant, produces a memory score significantly lower than all three of the rest of these. And so really all of these differences are significant. And that's it for this problem, and we will see you next time.